Welcome to Trigonometries. Today we're going to work on a related rates problem from calculus. The problem that we're going to work on is a word problem that says the following. A trough has ends shaped like isosceles triangles with width 3 meters and height 4 meters, and the trough is 10 meters long. Water is being pumped into the trough at a rate of 5 cubic meters per minute. At what rate does the height of the water change when the water is 1 meter deep? Now, to solve a related rates problem, what you're really looking for initially is what are all the quantities involved? And once you have all the quantities identified, you're going to find an equation that relates those quantities together. To get an equation that relates the rates of those quantities, you're going to take that equation and take its derivative implicitly with respect to time usually in order to identify how the rates are related to each other. For a problem like this that's based off of some kind of geometrical situation where water is being pumped in or out, the best way to start is by drawing a picture so that we can identify what quantities we actually need to deal with. So here we have a trough that looks like this. It has isosceles triangle ends, and it's basically like a prism of an isosceles with isosceles triangle cross section. So it's isosceles, meaning that these two edges are congruent in both the front and the back, all the way across. Now, water is being pumped into this trough, and the trough is filling up and is at some height. So we have something like that. So in order to identify what's going on, we kind of need to get an idea of like what quantities are at play. We know that the volume is changing by the water that's coming into the trough up here. And so one of the quantities that we need to work with is volume. So let's write that one down. So V is going to be the volume of water in the trough. The height of the water that's in the trough is going to be this value here, which we'll call H. So H is the height of the water. We know that that's an important quantity because we're being asked to find its rate. These are the two main quantities that we're looking for. We need to relate these quantities together. Now, other pieces of information that we've been provided with is how long the trough is. The trough is 10 meters long. So this distance from here to here is 10 meters. The overall height of the trough is 4 meters, and the width here is 3 meters. Now, in order to figure out how the volume relates to this, we need to know the volume of a prism, because that's essentially what this trough shape is. Now, the volume of a prism, regardless of what shape each side is, follows the same general principle. If the cross sections are the same all the way through, like in this case, it's an isosceles triangle, it's simply the area of the cross section times the height or length of the prism. So in this case, it'll be the area of this isosceles triangle times the length of the prism. Now, if we're only looking at the volume of the water, though, if it's not all the way filled, the triangle that we're actually looking for that's making up all the cross sections is this triangle there at any point where it's filled up a certain amount. So we actually need to get our hands on sort of what the area of that triangle is. So let's call that area there just AT. So the volume of this pyramid is going to be the area of that triangle, which we're going to get our hands on in a second, times the length of the trough, which in this case here will always be 10 meters, regardless of how full the thing is. So now we need to get our hands on sort of what the area of this blue triangle is going to be, given that the depth of the water is this H here. Well, the area of a triangle is equal to 1/2 the base times the height. We already have the height. That's what this H is. So that part we already know, or at least we have a variable for it. To get the base, we're going to need this line here. We're going to call B. So B is going to be the width of the water at the top as it fills up. Well, one useful tip whenever you're working a story problem in a class is that the story problems typically always have enough information to solve this. And so if you're kind of stuck on where to go with a word problem, look at the pieces of information that you haven't used yet and see if they can help you identify something about it. So here we need to get a formula for the base, and the pieces of information we haven't used yet is the fact that the overall side of the trough is 3 meters wide with a height that's 4 meters tall. What's happening here is that we basically have a triangle. It's an isosceles triangle that looks like this. We know that it's 3 this way and 4 this way, and the water level produces a triangle that's right here. Since this is an isosceles triangle, we know some things about the geometry of it. We know that these base angles are the same, and since this line here is parallel to that one, that tells us that these angles are also the same. This means that these two triangles are similar triangles, and so all their dimensions are all in proportion to each other. Ultimately, what we get, because these are similar triangles, is that this distance here to the height as a ratio is going to be the same as this distance here to its height. In other words, 3/4 has to be equal to B/H. We can solve that for B by multiplying the H over, and we get that B has to be equal to 3/4 H. And that'll be the case no matter how full the trough is. So this right here is what we're going to plug in for B, and we're going to end up with an equation that only has H in it. So this area formula here is going to be 1/2 times 3/4 H times H, and this will produce 3/8 H squared. And that's the area of the blue triangle here at any height H. This tells us that the volume here, we're going to get 10 times 3/8 H squared. Or we can cancel a 2 here with that, so we get a 5 now and a 4 there. This will be 15/4 H squared. That's the volume of the trough at any height H. So now we have a volume formula or an equation that relates the volume and the height, which are the two things that we have information about the rates on. We know how fast this is changing. We want to know how fast this is changing at a certain point. This equation here relates the two quantities. The derivative of that equation are going to relate the rates. So let's take the derivative of this with respect to time, because that's what rate we have with the volume. And we'll have to do that implicitly because there's no t in there right now. So on the left-hand side, we'll take the derivative with respect to time, get dv dt. Over here, we'll get the 15/4 because a constant just pops out when you take a derivative. The derivative of H squared is 2H, but then we have to multiply using the chain rule by the derivative of the H since it's a function of time implicitly. So this will give us a dH dt here. That's just the chain rule basically acting up. If you remember your work on implicit differentiation, that's the same thing that's happening here. This 2 will cancel with part of that 4 to make a 2 on the bottom, and we end up with the equation that dv dt is equal to 15/2 times H times dH dt. So now we need to put in information that we have. Well, we were told as part of the problem that the volume is pouring into the tank at a rate of 5 cubic meters per minute. So that tells us that dv dt is equal to 5 meters cubed over minute. It's positive because the volume is increasing. If water were leaking from the tank, we would use like a -5 because that means that the volume is going down. So what we're asked at this point is how fast is the height changing when the height is 1 meter deep? So once we filled up enough water to be 1 meter deep, how fast is the height of the water increasing? So that means we want to know what is dH dt when H is 1. And so basically what we're going to do is we're just now going to plug in all the things that we know and solve for the quantity that we want, which is the dH dt. Well, the dV dt is going to be this 5. The H is going to be equal to 1. And so we just plug everything in. So we get 5 is equal to 15/2 times 1 times dH dt. So on this side here, these two guys just multiply to 15/2 times the dH dt. So to solve for the dH dt, we just have to multiply by 2/15 to get rid of this. Multiplying both sides by 2/15 yield that dH dt is equal to 2/15 times 5. And of course, the 5 cancels with the 15 here to leave a 3 on the bottom, and you get that this is equal to 2/3. Now, what are the units? Well, H here had units of meters. T has units in minutes because that's what rate we used up here. And so this is going to have meters per minute. So what this tells us is that if water is pouring into this trough at a rate of 5 cubic meters per minute, when the height is 1 meter high for the water so far, then the height is changing at 2/3 meters per minute. So let's kind of recap just so you can see sort of the overall big picture of how to solve a related rates problem. So the first thing we did is we drew a picture that sort of illustrated what was going on in the problem. And that helped us identify the values of things that were important, and we labeled those with variables. Once you've identified those variables, one thing you could do, I waited until the end to write these down, but you could actually write down all the pieces of information you know. You know what dV dt was. You knew that the width here was 10 meters. You know that the width here was 3 and that the height was 4. You could write down all those things if you wanted to at the beginning so that you know what you have. Once you've identified sort of what you're looking for, which in this case here was how fast is the height changing, we know that what we need to relate is H and V because we wanted to find dH dt and we had information about dV dt. So we need to have some kind of relationship between the volume and the height. So now we start looking for a geometrical relationship between those two, which led us to the idea of what's the volume formula of this trough. And in that case here, we knew that our volume formula was going to rely on this area of a triangle, which led us to having to use some kind of geometry in order to figure out what that area formula was. Once we figured all that out, this geometrical idea led to this equation here, which shows how the volume is related to the height of the water. That right there is the relationship between the volume V and the height h of the water. Taking its derivative produces a relationship between the rates of change, and this is why we call it a related rates problem. This equation here is how the rates are related if this was how the volume and height were related in the first case. Now at this point, all you have to do is just plug in the information you know and solve for the dH dt as you go. And that's pretty much it for how you solve a related rates problem. I'd recommend actually trying another one yourself and referring back to this video if you need a little bit extra help. But that's it for today. We'll see you next time on Trigonometries.